These vertical acceleration problems, sometimes called elevator problems, just objects going up and down, accelerating in the vertical. And there's three parts to this. I'm going to do them sort of in parallel. So in other words, the way you pretty well always start off a force question is by examining the forces in a free body diagram. So I'll do that for part A, likewise in part B and part C. So there's the three elevators, same person every time. For the first elevator here, it looks like we're traveling at constant velocity. In other words, the acceleration is zero. Well, forces don't care about how fast you're going so much if you're traveling constant velocity. So according to Newton's first law, constant velocity, the forces here should give a net force of zero. So the tension, the elevator pulling upwards, the elevator cable, and gravity pulling downwards should be equal in magnitude. In other words, the net force is equal to zero. Now it's the same elevator each and every time, so each one should have the same force due to gravity acting on it, the same weight. So put that in. But here we're accelerating downwards at 1.1 meters per second squared. So that means gravity's pulling harder than the cable's pulling upwards. Now, some people like to use a plus-minus system for direction to establish your F net here. But, hey, the way I like to do it in tug of war is to say the F net is simply the larger force minus the smaller forces. I don't have to worry about plus-minus directional stuff at all. Doesn't matter. Now, here in part C, the motor's pulling a little harder, the tension is a bit greater, we're accelerating upwards. Ft, tension force, upwards. So in this case, the net force, the larger one, is the tension minus the smaller one. Now in a way, the physics is all done for each part. Now we just have to work the mathematics. So over here to work the mathematics, well, force due to gravity is m times g, of course. So our tension force, which doubles as the apparent weight of the person in there, is going to be the 80 kilograms of the person's mass times, and we'll use 9.81 as acceleration due to gravity here. So 80 times 9.81, 80 times 9.81 equals, and we get our apparent weight, in other words, the tension in the elevator cable here, like so. We'll round that off later. Now, here, the net force, the larger force minus the smaller force, where the net force is always, of course, m times a, force due to gravity is m times g, and tension we'll call the apparent weight. And of course, when you start going down in an elevator, you should feel a little bit lighter. So I hope this number is going to be a bit smaller than that one. Let's find out. So the tension, like so, is going to be mg minus ma. And so the apparent weight, Ft, that's 80 kilograms times 9.81 minus 80 kilograms, of course, times acceleration of 1.1, like so. Okay, 80 times 9.81. Well, I've already done that over here, of course. That's 784.8 newtons. 80 times 9.81 that is, sorry. 80 times 1.1 is 88 newtons. Subtract the two, and yes, it's a lower number than his normal everyday sort of weight, like so. You feel lighter when you start accelerating downwards in an elevator. You feel lighter. Great. Now here we're accelerating upwards in an elevator, and for those of us who are in elevators, all of us I hope, you feel a little bit heavier. So let's see what we get for the F sub t over here. So isolate what we're looking for, the apparent weight. I'm calling F sub t, like so, and that'll be the F net plus the force due to gravity. Ft equals F net. Well, we've already calculated F net, 1.1 times 80, so I don't have to run that through my calculator again. Force due to gravity, been there, done that, 784.8 newtons. So now these two combine. Let's see what they combine to give us. 784.8 plus 88 equals 872. 872.8 newtons. Yes, feeling a little heavier than normal. Remember, if you're traveling at constant velocity, that's essentially the same thing as stationary as far as forces are concerned. So now we have it here for what we need. And let's see what we get here, okay? So here, to the proper significant digits, part A, the tension force, or in other words, apparent weight, is 785 newtons. And over here, feeling a little lighter, going downwards, 697 newtons. And over here, going upwards, feeling a little bit heavier, Ft equals 873 newtons. For our final answers for part A, part B, part C.